simulate the response of this device. So what we have in this device, we have a polymer substrate, then we have a bottom electrode, then we have a piezoelectric layer, and then we have a top electrode. So in this forms of simulation process, we have a 3-step. One, geometry design. How we have to design the geometry? Once we design the geometry, then we have to define the material. Means for which layer, which material you require, you will define the material, and after that we will provide a boundary condition. Means where we have to fix the boundary, where you have to apply a perfect matching layer, where you have to apply the signal. So we will apply the boundary condition over the device, and then finally we will go for analysis part. Okay, so we have these 4 steps to perform analysis for any kind of device. So this is, we are having also multi-physics. So what we have here, if you want to go for designing a new device, then we will go to this model wizard. So once we click on model wizard, we have a different type. We can design different kind of devices: 1D device, 1D axis matrix, 2D device, 2D axis matrix, and 3D. So we will see today how we have to design 2D device. So we will click on this, and then we have to select physics. What kind of physics we require for our device? So let's suppose we require a structural mechanics, and in structural we require a piezoelectric device because we want to find out the analysis for my acoustic resonance. For that I need a structural mechanics, and in that I need a piezoelectric device. So I will select that piezoelectric device, and I will add this as a physics. Okay. Then I will go to study. So what kind of study I want to perform? So I will go to study. So here we have a different type of study: eigenfrequency analysis, frequency domain analysis, frequency domain model analysis. So as per your requirement, generally we use this eigenfrequency analysis to find out the different eigen mode of your device. So you can easily find out what will be the device frequency. And once you have idea about device frequency, because here we do not need to find out the eigen frequency, because we have idea based on my acoustic velocity of piezoelectric layer and thickness of the piezoelectric layer, I can easily find out my resonant frequency. So I need not to go for eigen frequency analysis. So I will select frequency domain analysis as my study, and then done. So what I did till now, I have selected what kind of geometry you want. So I select 2D geometry. Then what kind of mechanics you want. So in that I select physics as a piezoelectric devices, and then what kind of analysis required. So we selected a frequency domain analysis. Then next part comes geometry part. So in this geometry part, first we have to select length in meter. So generally these are the MEMS devices, and what is the device size? Always in micron. So we will select here, instead of meter we will select micrometer. Then what is my structure of the device? What I have this PD substrate, over which I have a aluminum layer. So first we have to decide the thickness of all these. So let's suppose your thickness of PD substrate is 100 micron. Then 150 nanometer is my bottom electrode thickness, and then I have a 2 micron thickness of my ZF layer, and 150 nanometer is my top electrode layer thickness. So what I will do, I will design my geometry. So here I will right click, and I will select a rectangular, and I have to decide what is the width and height. So what is width I require? I require a 1000 micron width. And what height I required? I required a 100 micron height. And what is the x and y? X and y is my starting point of the geometry. Then I will select field selected. So this is my silicon PET substrate. So what I have created my PET substrate. After that, what I need? I need bottom electrode. So for that bottom electrode, again, what I will do? I have to either I can right click on this rectangular one, or I can create a duplicate one, or either I directly right click on geometry and again I will select rectangular. And again, what is the width? Width is fixed 1000 micron. So width for my bottom electrode is 1000. But what is the height I required? Height I required 150 nanometer. So 150 nanometer means 0.15 micron. So my height is 0.15 micron. But what is your x? X is 0. But what is y? What should be y? Because you want to deposit this metal oxide over your silicon PET substrate. So already you have 100 micron your PET substrate. So you want to deposit this over the PET substrate. So what is your y? Y is 100. So then I will select build selected. So what I have, if you zoom out this, you have this PET substrate, and over the PET substrate you have C. This is your PET substrate, and over the PET substrate you have a bottom electrode. Then next we have to have a piezoelectric layer, that is ZNO layer. So for ZNO layer, again what you require? You require a width 1000 and height. What height required? We require 2 micron thickness for my ZNO layer. So instead of 0.15, I will select 2. And what is my height again? Instead of 100, now my height is 100.15, because height of your substrate plus height of your bottom electrode. So 100 plus 0.15, and I will click on this build selected. So I created my piezoelectric layer. Now what I need? I need a top electrode. So top electrode, again I will create a duplicate, and instead of 1000 micron I will select 750 nanometer as a width of my top electrode, and height is my 0.15. Okay. Then what will be the height y? Y 100 plus 0.55 or 0.15 plus 2 micron, whatever the thickness of your ZNO layer. And then I will now see what is your x. Now your x is not 0, because instead of selecting 1000 micrometer width for your top electrode, I selected a width of 750. So 250 I have to reduce from left hand side, and 125 I need to reduce from left hand side, and 125 I need to reduce from right hand side. So from where I need to start? I need to start from 125 micron. So instead of 0, I will select 125, and then I will click on build all. So here you can see this is your top electrode, piezoelectric layer, bottom electrode, and PET substrate. Understand? So like that, yeah, but it is not visible. So for that we have an option here. Once we go into a geometry, and it will go to view, access, and once we click here, Yeah. So I click on this preserve aspect ratio, so it will be looking like somewhat what we can easily visualize our device. Otherwise, in previous case we are not able to visualize. So what we have in this device now, we have this top electrode, ZNO layer, bottom electrode, and PET substrate. So now what I need to do, I need to assign a material. Because my geometry part done, now I need to assign material. So for that I will go to this material and I will right click and add material. So for that add material, I have so many materials. I will go to MEMS, and in MEMS I have so many materials. So first what I need a polymer substrate. So I will go to polymer, and in this I have a PET substrate, that is polyethylene. So this is my PET substrate, or if you want you can search here also. Here search option is also there. So you can select material from here also. Clear? So you can go and select whatever you want from here also. So for example, we have this PET, so add to selection. So once you click on add to selection, it will come to your material part. Clear? Then what? It requires some property. Okay. Then what we need? Another material. What kind of material I require? So I have to select this one is my. So this one is what? This one is my PET, and what about others? This is not my PET, so I will remove this from here, and this is not. This is my ZNO layer, so this is not PET, and again this is what? This is my drop electrode, so I will remove. So I have this is as my PET substrate. Then what I need to do? Again I have to select my next material. So what is my next material is bottom electrode. So for let's suppose my bottom electrode is gold. So I'll go to again I will right click here and go to add material, and once I go to MEMS, there I have a metal. So in metal I have a different kind of metal. I can select gold as a metal. So I click on gold, and I need to define a layer. Which layer is my gold layer? So I have this as a gold layer, and this one, so this is the PET, this is, so I define these two materials as my electrode, and then what left? Piezoelectric layer. So I have to define piezoelectric layer as a ZNO. I will go to material and go into MEMS. In this MEMS I have a, where I have a material semiconductor, and what I need a ZNO. So where I will get this ZNO? In insulator. So this is zinc oxide. I will right click and click here. So this is my ZNO layer. Okay. After that, we require this property. Why it is asking about this property? Because we have to define the physics for that. According to that, so what we require in this physics. So here we have to define the so many things. So we will see another simulation, so we can finish it quite soon. So what we have here, this is the device, and we define the physics. So what physics we require? First we define which is the my elastic material. So I have this top electrode and bottom electrode. I will consider as elastic and substrate as elastic, and only my piezoelectric layer is my piezoelectric layer or piezoelectric material. All material, remaining all materials are elastic. Then I have to define ground and terminal. So I define ground over the bottom electrode. So this is my selection of ground, and I will define 1 volt to my top electrode because I want to excite, because it is working on the base of inverse piezoelectric effect. What it says, once you apply a voltage, it generates a state, and due to this state, mechanical wave travel into your piezoelectric layer, and due to this, you have a generation of resonant mode. So we define this terminal voltage 1, and then we define a fixed constant. We are keeping side boundaries of my resonator fixed, and we provide a elastic, or we can easily vibrate. So bottom side and top side is free. Otherwise, left hand side and right hand side I fix so that it can easily resonate. And then I define this PET substrate as a linear elastic material. So this is done. So once you define this physics, then there is no error in your material property. Clear? So now what we have done? We have done geometry, we define the material, and we define the physics. Then after that, what we need to do? We do the meshing. Why we require meshing? To calculate the small portion of my device. So for that, I have to apply meshing. So once I will click and click on build. So you can use any type of meshing according to your required. Otherwise, you can choose this user control meshing. Otherwise, you have your own meshing you can also apply. So if you want to your own meshing, then you can go here and you have to apply different type of meshing also. Clear? Then we also need to define some PML layer, left and right side, so there is no reflection of your acoustic signal outside the device. So here you can see this portion is your PML layer. That is perfect meshing layer. Left hand side and right hand side, both sides. So we define this PML layer. Where we will define? We define this PML layer in here. So see, this is my PML layer. So in this, here we define the PML layer. So after that, defining the PML layer, what I have to go for analysis. So for that, I am going to study. What kind of study I selected? I selected frequency domain analysis. So in this frequency domain analysis, what I need to do? I have to provide the frequency range. In this frequency range, you want to perform your analysis over your device, because you know what is the resonant frequency of your device. So it should be selected. For example, your resonant frequency is 2.4 GHz. So you have to select this frequency range between 2 to 3 GHz. Clear? So you can easily visualize your performance. So based on my thickness of dead layer, because I selected dead as a 2 micron. So what I will get based on this, because 5380 is my acoustic velocity and 2 micron is my thickness. So 5630 divided by 2 into 3. So 5630 divided by 6. According to that, I will get my resonant frequency. So based on that, I select the range of my frequency spectrum. So I selected 1.29 GHz to 1.42 GHz, and I select step size of 1 MHz. If you keep your step size smaller, you can see a very smooth performance of your resonator, but it requires a time. If you do not have a time, you can select the step size larger one also. Clear? Then once you define, then you have to go for click on this study and to click here compute. So once you click on compute, it will start the analysis of your device. So once this device analysis will finish, then in result section you can see the displacement of your device. So here you can see the displacement of your device. So here you can see there is the perfect confinement of your acoustic signal within the piezoelectric layer. And then after that, we want to see the performance of the. So for performance, what you need to do, you have to go to result, right click, and you have to select 1D plot group. And in 1D plot group, what you need to do, 1D plot group, you have to right click and you have to go to global. And in global, you have to find which solution, for which solution you want, and then you have to go to this result. So here you have a different result. So for example, I want this admittance curve or response of mine. So what kind of response you want? You want absolute response. So I want to find out impedance versus frequency. But what is this? This is my admittance versus frequency graph. Clear? What is this? My admittance versus frequency graph. But what I want? Impedance versus. Sir, you told me why you are taking log value. If you are not taking log value, our response is like that. So there is very small dip is there in resonant frequency. So if you take this as a logarithmic graph, we have a sharp dip for my resonant frequency and endo-resonant frequency. So now you can see this is my frequency response for the range of 1.29 to 1.42 megahertz. Clear? Then if you want to find out the quality factor, so all you can find out with the help of, you have to create different plotting group and you have to find out all these values. Clear? So this is all about very simple. And if you are having a zero knowledge, if you want to start with space, so many applications available inbuilt into your console software. So you can learn step by step. So this is the quality factor versus frequency. So for example, here you can see ohm, definition, geometry, physics, math, study, result. So in this, where I will find out my different applications. So here you can see model library. For example, I am new to this device. So how I can start? So for that you can go to model library, and in this model library you have so many structures. What kind of structure you want? So let's suppose I want to go for this bulk acoustic resonator. So in MEMS module, once you go, you have an actuator, microfluidics, piezoelectric devices. What we want? We want piezoelectric devices. So once you go to piezoelectric devices, you have a composite transducer, you have a piezoceramic tube, you have a shear bender, you have a thickness shear part. So that is your part oscillator, and this is your thick film bow resonator. What you can do? You just have to double click on this, and either you can open this PDF document. If you want to replicate this, what you can do, have an option here. Either you can open directly this model and see how you have to analyze your model, or either you have an option, you can open the PDF document also. So in this PDF document, what you have, all the application similar systems are there. So see here, this is your 3D view of your device. So what you have this silicon substrate, and this is your bottom electrode, this is your bearing layer, and this is your top electrode. So what we are doing, we are taking cross-sectional view of this, and we are simulating the 2D geometry of this device. Clear? So you can easily perform the steps. You have seen, once you go through here, you have a different step. So this is the cross-sectional view of your device. So you have to select different layer for your device, and then you can see here boundary, what kind of boundary you have to define. So everything is available in the step-by-step form. So you can easily go through this. So see here, all steps, first you have to create the geometry, then after geometry, what you need to do, you have to define a PML layer. So how you have to define. So all steps one by one you have to available. So you need not to worry. You are interested in MEMS space capacitor, you are interested in MEMS space transistor. So anything you can do, start with scratch. You have everything in step by step. Clear? And also this geometry directly available. So for example, I am new. Even I am not replicate this device with the help of step. Then what I can do? I can go to this open model. So if I see open model, at least I can replicate this model. So once I will see from this how to apply different physics, how to apply material. So see, once you go here you have a geometry. So how you have to build the geometry? So you can click here what should be your width, what should be height of your device. Then how to define material. So you can have an idea how to define material. Then how to define physics. So here you have a boundary condition, how you have to define. So you can easily understand by opening the particular model, and then how you have to define the meshing, and then how you have to do. So we have two type of analysis, either frequency and frequency domain, and with the help of study you can click compute and you have to do the analysis. So you can do anything whatever you want. Okay, so if you have any question you can ask. If any query from your side, so you can download this and you can start your simulation if you want for your attack PhD. Oh, bottom and top. It's depending on you. Yeah, any combination you can use. It's your choice. Like that I selected bottom electrode as aluminum and top electrode as gold. Why? Because top electrode I want to use for sensing. If I will use aluminum and over the aluminum I will use metal oxide layer. Then what will happen? My top electrode also exposed to oxidation and it will become an oxide. So for top electrode I have to always select gold, not a aluminum. But bottom electrode you can choose aluminum.
Thank you, sir, for giving such a good session and a very nice session. I invited to Vandana Kare madam. He gives us a vote of thanks to Madam Professor.
Good evening, everyone. I think everyone wants to go home. Now I think 5 o'clock, everyone is thinking in that way. But what I am saying, what Dr. Raju Patel sir, he delivered nicely whatever he delivered with respect to our VLSI, and he actually delivered today about AI-driven optimization. So whatever work we are doing in terms of research, optimization is very important part. Like our principal sir said, he will prepare one antenna after this session. He will also optimize in this respect, whatever sir delivered. So it is really a good thing. In the same manner, I am telling to all of you who have attended the full session, they can also try something and optimize in proper way. Sir actually discussed about materials also, and the simulation part, he said that he cleared very nicely. So such type of things are required for everyone, not for EC students or EC faculty. For all, whoever wants to do related to this field, they can approach for this. So once one big clap for sir. And, thank you sir. We will give another time also opportunity for you to come and deliver something new for us. Thank you sir. Thank you very much. And thank you for all faculty members. They listen patiently. Thank you very much.